Before we begin, make sure you subscribe and turn on notifications, because the next discoveries from this mission could rewrite everything we know about life in the universe, and you won't want to miss it. Somewhere nearly 600 million kilometers away, orbiting the largest planet in our solar system, there is a moon covered in ice. At first glance, it looks silent, frozen, lifeless. But beneath that icy shell, scientists believe there may be a vast global ocean, dark, deep, and potentially alive. This is Europa. For decades, Europa was just another moon in Jupiter's orbit. But today, it stands at the center of one of NASA's most important missions. A spacecraft has been built and sent across the solar system to investigate a simple but profound question. Is there life on Jupiter's moon? This is not science fiction, and this is real exploration. And the answer could change humanity forever. Europa, the moon that shouldn't have an ocean. Europa is slightly smaller than Earth's moon, yet it holds one of the greatest mysteries in planetary science. Its surface is covered in a thick layer of water ice, crisscrossed with long, dark streaks and fractured lines. Unlike heavily cratered moons that show scars from billions of years of impacts, Europa's surface appears relatively smooth and geologically young. Something is reshaping it from below. When spacecraft first flew past Europa in the late 20th century, scientists noticed that its surface looked like cracked sea ice on Earth. The pattern suggested movement beneath the crust. Later, magnetic field measurements revealed something even more astonishing. Europa appears to have a conductive layer beneath its surface. The most likely explanation for that conductivity is salt water. Liquid salt water. Far from the sun, in an environment that should be frozen solid, Europa may hide a global ocean beneath tens of kilometers of ice. That ocean could contain more water than all of Earth's oceans combined. But how can water remain liquid so far from solar warmth? The answer lies in gravity. Europa is constantly stretched and squeezed by Jupiter's immense gravitational pull. Its orbit is slightly elliptical, meaning its distance from Jupiter changes as it travels. As it moves closer and farther away, tidal forces flex the moon's interior. That constant flexing generates heat through friction, warming the interior enough to keep an ocean liquid beneath the frozen shell. This process is called tidal heating, and it may be the key to Europa's potential habitability. An ocean in the dark. If Europa truly has a global ocean beneath its ice, then it is one of the most intriguing environments in the solar system. On Earth, wherever liquid water exists, life tends to follow. Even in the most extreme conditions, deep-sea hydrothermal vents, subglacial Antarctic lakes, and volcanic hot springs, life has adapted. On the ocean floor of Earth, entire ecosystems thrive in total darkness around hydrothermal vents. These ecosystems do not rely on sunlight. They rely on chemical energy released from interactions between water and rock. If Europa's ocean touches a rocky seafloor, similar chemical reactions could occur. That interaction could generate energy. And where there is water, energy, and the right chemistry, the possibility of life becomes scientifically plausible. No one expects complex civilizations beneath Europa's ice. If life exists, it would likely be microbial. Simple, microscopic, but even the discovery of a single alien microbe would transform our understanding of biology. It would mean life emerged independently in more than one place in our solar system. That would suggest life is not rare. It would suggest life might be common. The plumes that changed everything. In recent years, telescopes detected what appeared to be plumes of water vapor erupting from Europa's surface. These observations suggested that material from the subsurface ocean might be escaping through cracks in the ice. If confirmed, this changes everything. Instead of drilling through kilometers of frozen crust, a spacecraft could potentially fly through these plumes and sample material directly. That material could contain salts, organic compounds, and perhaps chemical signatures associated with biological processes. It is as if Europa is offering a sample of its hidden ocean to space, and NASA is preparing to collect it. NASA's Europa Clipper mission. NASA's Europa Clipper mission represents one of the most sophisticated planetary science efforts ever launched. Rather than landing immediately, Clipper will orbit Jupiter and perform dozens of close flybys of Europa. This strategy is deliberate. Jupiter's radiation environment is intense. High-energy particles trapped in its magnetic field can damage spacecraft systems. By making repeated flybys instead of remaining in constant orbit around Europa, the spacecraft reduces radiation exposure while gathering detailed data. Europa Clipper carries powerful instruments designed to peer beneath the surface and analyze the moon's composition. Ice-penetrating radar will estimate the thickness of the ice shell. Thermal imaging will search for warmer regions that might indicate active processes. Spectrometers will analyze the surface chemistry in extraordinary detail. Magnetic measurements will help determine the depth and salinity of the subsurface ocean. The mission's goal is not to announce alien life overnight. Its objective is to determine whether Europa is truly habitable. Is there liquid water? Is there energy? Are there the necessary chemical ingredients? If the answer to those questions is yes, the next step could involve sending a lander in the future. Radiation and chemistry. Europa's surface is bombarded by radiation from Jupiter. At first, this seems like a barrier to life. The surface environment is harsh, cold, and chemically altered by energetic particles. But radiation may also contribute to habitability. When radiation interacts with ice, it can produce oxidants, chemically reactive compounds. If cracks in the ice allow surface material to mix with the subsurface ocean, those oxidants could provide chemical energy to potential life below. In this way, Jupiter's radiation could act as both a threat and a resource. The surface may be hostile, but the ocean beneath might be protected and chemically energized. What would proof look like? Scientists are not looking for swimming alien creatures beneath the ice. They are searching for chemical imbalances that suggest metabolism. They are searching for complex organic molecules that cannot be easily explained by geology alone. Life leaves patterns. On Earth, biological processes alter their surroundings in measurable ways. Certain combinations of gases, molecular structures, or isotopic ratios can signal biological activity. If Europa Clipper detects compelling evidence of these patterns, it would justify future missions designed to go even further. The search is not about speculation. It is about measurable data. The bigger question: Europa is part of a broader category known as ocean worlds. Other moons in the solar system, such as Enceladus and Titan, also show evidence of subsurface oceans. But Europa remains one of the most promising candidates for life because of its size, ocean depth, and potential interaction between water and rock. And if life is discovered on Europa, it would imply that life emerged independently at least twice in our solar system, once on Earth and once beneath Europa's ice. That would suggest life is not an extraordinary accident. It would suggest the universe may be filled with living worlds. And if Europa turns out to be sterile despite having water and energy, that would also teach us something profound about the conditions required for life to begin. Either outcome reshapes our understanding of existence. Waiting for answers. Europa Clipper is expected to reach Jupiter in the early 2030s. Once operational, it will begin years of close flybys, gathering data and transmitting it back to Earth across hundreds of millions of kilometers. Every image, every spectrum, and every magnetic reading will bring us closer to answering one of humanity's oldest questions. Are we alone? Europa may not provide the final answer immediately, but it may give us the strongest evidence yet that life can exist beyond Earth. Beneath that frozen crust, in a dark and silent ocean, something may be stirring, and for the first time in history, we are finally close enough to find out. The ice shell, barrier, or bridge. Europa's frozen exterior is not just a layer of ice. It is a dynamic shell shaped by internal forces. High-resolution imagery has revealed ridges that stretch for hundreds of kilometers, chaotic terrain where ice blocks appear rotated and refrozen, and long fractures that cut across the surface like scars. these features are not random. They suggest motion beneath the ice. Some regions look as if the surface cracked open, shifted, and then refroze. This process implies that the ice shell may be floating on a liquid ocean. If the shell is thin enough in certain areas, material from below could rise upward. Conversely, surface materials might sink downward. That exchange is critical. If oxidants created by radiation on the surface mix with the ocean below, they could provide chemical energy. If nutrients from the rocky seafloor rise upward, they could fuel biological processes. The thickness of the ice shell remains one of the most important unknowns. Some models suggest it could be around 15 to 25 kilometers thick. Other estimates propose thinner regions. Europa Clipper's ice-penetrating radar will attempt to map these variations. If there are thinner zones or subsurface lakes embedded within the ice, those could become future landing targets. Areas where the ice interacts directly with the ocean would be especially valuable for exploration. Europa's shell may not be a simple barrier. It may be a bridge between the ocean and space. The ocean's chemistry, ingredients for life as we understand it. 3 broad requirements must exist: liquid water, an energy source, and the right chemistry. Evidence increasingly supports the presence of liquid water beneath Europa's surface. Tidal heating provides a continuous energy source. The remaining question centers on chemistry. Spectroscopic observations of Europa's surface have detected salts, possibly magnesium sulfate and sodium chloride, which are consistent with ocean material reaching the surface. If ocean water is salty, that increases its conductivity and supports magnetic measurements indicating a subsurface ocean. More importantly, interaction between water and a rocky mantle could create hydrothermal systems. On Earth, hydrothermal vents release minerals and chemical compounds into surrounding water. Microorganisms feed on these chemicals in ecosystems that exist entirely without sunlight. If Europa's ocean is in contact with rock, similar processes could occur. Chemical gradients could develop. Nutrients could circulate. Life does not require sunlight. It requires chemistry, and Europa appears to have the essential ingredients. Jupiter's influence, a hostile giant. Europa orbits within Jupiter's powerful magnetic field. The radiation environment near Jupiter is intense enough to damage spacecraft electronics and would be lethal to unprotected humans. At first glance, this radiation seems like a negative factor for habitability. However, beneath the ice, the ocean would be shielded from much of this radiation. The thick ice shell acts as protection. At the same time, radiation striking the surface ice creates oxidants and other reactive compounds. If geological processes transport these materials downward into the ocean, they could contribute to chemical energy sources. Jupiter's immense gravity is also responsible for Europa's internal heating. Without tidal flexing caused by Jupiter's gravitational pull, Europa's ocean would likely have frozen solid long ago. In this sense, Jupiter is both a threat and a provider. Its radiation is harsh, but its gravity sustains the ocean. Europa exists in a delicate balance shaped by its giant host planet. The challenge of exploration. Exploring Europa is not simple. The distance alone presents enormous technical challenges. Signals from Jupiter take roughly 30 to 50 minutes to travel one way between Earth and the spacecraft. Depending on orbital positions, that delay means Europa Clipper must operate autonomously during flybys. Radiation hardening is another major challenge. Spacecraft systems must be shielded to survive repeated passes through Jupiter's radiation belts. Engineers have designed protective vaults around sensitive electronics to reduce damage. Data transmission is limited by distance and power constraints. Every measurement must be prioritized. Instruments must gather precise data in short windows during close flybys. Unlike missions to Mars, where rovers can explore continuously, Europa Clipper will make rapid passes, collecting data in bursts. Each flyby is a brief opportunity to gather clues from a world that may hold profound answers. What a future lander could do. If Europa Clipper confirms that the Moon's ocean is habitable, the next logical step would be a lander mission. Landing on Europa would require navigating intense radiation, icy terrain, and extreme cold. Any lander would need to be sterilized carefully to avoid contaminating the environment with Earth microbes. Planetary protection protocols would be strict. A lander could analyze surface chemistry directly. It could drill shallow samples from the ice and search for organic molecules. It could test whether complex carbon compounds exist. A more ambitious mission might involve a cryobot, a robotic probe designed to melt through the ice shell and reach the ocean below. That concept remains technologically challenging and decades away, but it represents the ultimate goal: to directly explore an alien ocean, to send a robotic explorer into dark waters that have never seen sunlight. That would be one of the most extraordinary achievements in human history. The possibility of failure. Science advances not only through discovery, but through elimination. It is possible that Europa Clipper will find strong evidence of an ocean, but no compelling signs of biological chemistry. It is possible that the ocean exists, but lacks sufficient energy exchange. It is possible that life never emerged there. Even that outcome would be significant. If Europa has water and energy yet remains lifeless, scientists would need to reassess how rare life truly is. And it would suggest that the origin of life may require additional factors we do not yet understand. Every outcome refines our knowledge. Europa is not simply about finding aliens. It is about understanding the conditions under which life begins. A cosmic turning point. For most of human history, the question of life beyond Earth was philosophical. Then it became astronomical. Now it is experimental. We have identified thousands of exoplanets orbiting distant stars. Many may contain oceans, but they are too far away to sample directly. Europa is different. It is within reach. It offers a nearby laboratory for testing one of humanity's deepest questions. If life exists beneath Europa's ice, it would mean biology is not unique to Earth. It would mean life can arise in darkness, powered by chemistry, far from sunlight. That realization would reshape biology, astronomy, and even philosophy. Waiting for the signal. In the coming decade, Europa Clipper will begin its detailed investigation. Data will stream back across millions of kilometers. Scientists will analyze ice thickness, ocean depth, surface chemistry, and magnetic signatures. Each discovery will build toward an answer. Is there life on Jupiter's moon? Europa has kept its ocean hidden for billions of years. Soon, humanity will finally have the tools to peer beneath the ice. And when that first clear signal arrives, whether it confirms life or deepens the mystery, it will mark a new chapter in our understanding of the universe. We are not just exploring a moon. We are testing the boundaries of life itself.